Good afternoon, and welcome to this science break session on rocky rocks and shaky earthquakes with Dr. Anna Rood. My name is Hilary Glassman-Deal, and I'll be chairing today's session. Briefly, I'm not a scientist. I work at Imperial Centre for Academic English, and I met Anna through our work at the centre to support the research outputs and research communication at Imperial across the college. As part of our provision, we offer one-to-one consultation and editing support for all types of research communication, particularly papers, helping writers to write more effectively. I guess to produce a clear and readable paper, and very importantly, to speed up the writing process so that it doesn't get caught in endless rewrites. We work with early stage researchers who are struggling with their first paper, with research groups who are collaborating to produce a paper, doctoral students writing the thesis, and veteran researchers who are writing papers that are clearly headed for high impact journals and which are likely to be able to change the direction of research in their area. Anna contacted me to work with her and Dylan on crafting their paper to report this, I was going to say groundbreaking research, but actually the important thing is about not groundbreaking. Even to me as a non-scientist, it was clear that this study deciphering the long-term earthquake history to inform earthquake prediction had wide-reaching significance in a very wide range of areas. As I understand it, Anna and her 10 co-authors from a range of disciplines were essentially investigating a kind of classic why didn't the dog bark question, like the Sherlock Holmes question of how come the dog didn't bark, why did nothing happen? And also they were trying to look at how long, and if this particular event, not the dog, but in their case the rock, the toppling rock hadn't toppled for. So in that context, why hasn't this precariously balanced rock been toppled? How long has it been standing there in that position? And of course, how to use that data to inform earthquake prediction and critically also the construction of high value new facilities, civil engineering facilities that need to withstand catastrophic earthquakes. So the knowledge they've gained has implications for earthquake hazard assessment and also for many civil engineering applications. For example, it can provide key input to estimate the cost of safe construction of nuclear power plants, dams, bridges. Essentially, this study has potentially whacked the timescale of information for earthquake prediction from hundreds of years to tens of thousands of years. So in that sense, I guess it's truly groundbreaking. Essentially, they are recording a major earthquake that hasn't happened. Anna's background is in geology. She did her undergraduate degree here at Imperial, and then she went on to do her PhD in the Department of Civil and Environmental Engineering. This fusion, bringing together of geology and engineering, underpins and informs her work, and it's a constant theme for her in her research. Her work is truly multidisciplinary, and it integrates data across the geosciences, geo and radiochemistry, nuclear physics, geohazard assessment, and it therefore has value across these disciplines academically, as well as in the more practical civil engineering applications I mentioned before. Anna is also the Deputy Laboratory Manager of the COSMIC Laboratory, which is Imperial's state-of-the-art cosmogenic nuclide research facility. And in fact, the rock samples in her studies were processed at the COSMIC Lab to determine how many thousands of years they had been exposed at the Earth's surface, which has been a powerful component of the study. If there's time at the end, Anna will also talk about the next directions for research, and she'll take questions at the end of the session. So please post your questions as you think of them as she goes through today. Before we begin, I just want to deal with a few technical points regarding how those questions will work. If you want to post a question for Anna, you need to use the Q&A button. If I'm correct, that's the one with a question mark on it at the side of your screen. Also, please note that the event is being recorded. So if you don't want your name read out with your question, that's absolutely fine. Just submit it anonymously. You will be able to see the questions that other people have asked. So it's quite helpful if you like a question by giving it a thumbs up, so that we know which questions seem to have the most interest and we can prioritize those at the end of the session. So that's all from me. I'd now like to hand over to Dr. Anna Rood. Anna.
Okay, thank you so much, Hilary, for your kind introduction, and thank you everyone attending for joining me today for my talk. And so I'll be talking about my PhD research that I'm currently completing. And so I use the strange preservation of these precariously balanced rocky rocks to use them as a validation test of somewhat shaky earthquake estimates that are thought to happen in seismically active areas. And so the aim of my research is to make these estimates more certain, to improve them for society. And so I'll be talking about a couple of studies and some rocks from both these studies in my talk. So the first one is where I applied these methods to validate the earthquake hazard estimate for a nuclear power plant site in Central California. And so a quick shout out to all my co-authors for their contributions to that study. So as well as this study, I'll also be talking about some rocks that I'm currently working on all around Southern California that I'm using to validate earthquake shaking estimates for the San Andreas faults there. So before I get into the rocky rocks, I thought it'd be first important to talk about the societal question that we're trying to address here. And so let's first, I think, explore the brilliant pun that is shaky earthquakes. And so future earthquake shaking estimates in seismically active areas, they're made using the earthquake data that we've recorded of earthquakes that have happened in the past, and then extrapolating that into the future. However, the problem is that seismometers that we use to record earthquakes have only been recording these earthquakes for the past couple of hundreds of years. So the earthquakes that happened thousands or tens of thousands of years ago are highly uncertain. So when we then flip that and try and make estimates that far into the future, they become really uncertain. And so this is a really big problem, because these earthquake shaking estimates, as Hilary was saying, are used in the design criteria of critical infrastructures such as nuclear power plants. They make national hazard maps. They dictate your earthquake insurance rates. And so the fact that they're so uncertain is a really big problem. So as I said, the aim of my research is to reduce this uncertainty. And so the specific type of uncertainty we're trying to reduce is called epistemic uncertainty. But all that really means is that it arises due to our lack of data or understanding about a particular subject. And so in earthquake science, we want to consider and combine all that uncertainty. So we do that using a framework called probabilistic seismic hazard assessment, or PSHA, as I'll probably end up referring to it as. And so we consider and combine all these uncertainties and all the different values that we think parameters might have into what we call a logic tree. And so I'm just going to walk us through a really simple example to show how these uncertainties just combine in these analyses. So first of all, we've got our nuclear power plant sites. The first thing we want to know is, where are the active faults that are going to cause large ground shaking events to our site? And so in our nuclear power plant site, this is especially difficult because in order to access cooling water, nuclear power plants are usually on the coast. So therefore, the active faults are going to be offshore, making it even more difficult to study them to understand their behavior. So we send out our geology team to do a study of the local faults. And so they have 3 different techniques that they can use to decide which faults are active versus inactive. And so because we don't know which one of these ways of characterizing the faults is correct, we say this has epistemic uncertainty. We don't know which one of these 3 ways is correct, so we consider all 3 as an alternative branch through our logic tree. So the second thing we now want to know is, what's the seismicity rate on those faults? How often do earthquakes of certain sizes occur? Again, we've got a situation where there's three different ways, three different models you can use to describe that behavior. We don't know which one's correct, so we consider all three. This parameter has epistemic uncertainty. So I've drawn it out here for just the first way of thinking about the earthquake sources. But the way this is actually combined is that I draw all three rates branches coming out of each of these seismic sources. So you're considering all possible combinations. And so the third thing in this simple example now is we want to know how the earthquake energy travels from our seismic sources to our site of interest. And we do that using what we call ground motion models. And so these are mathematical equations derived from recorded earthquake ground shaking events. And in this case, we've got 5 different ways that you could regress that data to get an equation to describe that energy traveling. So even in this really simple example where we're just considering 3 parameters, if we drew out through each of the branches, through each of the logic tree, we would end up with 45 different hazard estimates of what we think the true ground shaking at our nuclear power plant would be. So there's not a firm understanding about what the shaking will be at the site and therefore the structure. And so this is just a simple example, but for real logic trees, for real structures, there can be a million alternative branches through these logic trees. So a million different ways of which we might think the ground will shake at that site. And so this is an output for one of those PSHA models. So each one of those alternative branches through the logic tree ends up as a hazard curve on this plot. And so when you've got millions of hazard curves, they're quite often plotted as fractals, as they're shown here. And so this plot has on the x-axis down here, peak ground acceleration, which is the maximum acceleration of the ground during an earthquake shaking event. And that's in units of gravity. So once you exceed a value of 1 here, you've exceeded gravity. So rocks or objects can be thrown up into the air at that point. Then on the y-axis here, you've got the annual frequency with which that level of ground shaking is estimated to occur. So you can think of these numbers on the axis here as 1 over the average time between an earthquake shaking event. So this 10 to the minus 4 here is the 1 in 10,000 year earthquake. And so this 1 in 10,000 year earthquake is really important for the required design criteria of critical infrastructure, such as your nuclear power plants and dams. And so this blue curve here, this is the mean curve. So the mean estimate from, if you took all those branches and took the average, this is what you'd get. And so it's estimating that you get a ground shaking of 1 G, so equal to the force of gravity every 10,000 years. And these curves are the shape such that smaller earthquakes are happening more frequently and larger earthquakes are rarer. And so we have our mean hazard curve. But you can see in all these other fractals that are plotted, we have a large uncertainty around that average estimate. And so in this case, I've circled here the range between the 5th estimate and the 95th estimate. And so this ranges from a ground shaking of 0.5 G, which would cause maybe substantial damage to your structure, all the way up to 1.5 G. So you're exceeding gravity. This is going to be devastating to your structure. As the fact that there's huge uncertainty down in this area is in part due to the fact that the data that is input into these models is collected from seismometers, which are only sampling the very top part of this graph and then extrapolating it downwards. And so the estimates down here are highly uncertain and untested. So ideally what we do in this situation is we run an experiment where we place a seismometer at our site and record all the earthquakes that happened for 10,000 years. And then we'd really know this answer down here. But the point is that the data from that experiment is still a long way off. But luckily, we have some ancient, preserved, fragile geologic features which have done all that hard work for us. So that's where our rocking rocks come in. So precariously balanced rocks are boulders that are separated from their pedestal on which they sit, which means they're able to rock backwards and forwards during an earthquake ground shaking event. And ultimately, they can potentially topple over if that level of ground shaking is large enough. And so we refer to them as inverse seismometers, as unlike seismometers here on the left that record the earthquakes that have happened, our precariously balanced rocks record the earthquakes that have not happened. Specifically, they've recorded the rare large earthquakes that have not happened because they would have been so large they would have caused the rock to have toppled over. But we see it's still standing there, so it can't have happened. Another key difference between our seismometers and inverse seismometers is the timescales over which they're recording. So our seismometers, as I said earlier, only been recording for the past couple of hundreds of years. Whereas our precariously balanced rocks, our inverse seismometers, as we'll see later, they've been recording for thousands or tens of thousands of years. In order to use our precariously balanced rocks to inform our earthquake estimates, we need to get two pieces of data from them. The first is we want to know how fragile the rock is. And so what we mean there is we want to know how likely that rock is to fall over given a certain strength, low, medium, high of earthquake ground shaking. Second thing we want to know is how long that rock has been precariously balanced in the landscape. So how old it is, how long it's been recording this lack of large earthquakes. And so once we get these two pieces of information, we're going to combine them together and then individually test each and every one of those branches through the hazard logic tree to see which one of those branches are consistent with our rock still standing and which ones are inconsistent with our rock still standing. So let's answer the first question first. How fragile is the rock? As this essentially comes down to the geometry of the rock, where intuitively taller, narrower rocks are going to be more likely to topple over during weak earthquake ground shaking than, say, a wide, short, squat rock. And so in our analysis, we simplify our rocks just down to a two-dimensional slice through the rock, where we include its center of mass, and importantly on the bottom, these rocking points, which are where it's going to rock backwards and forwards during when the ground's shaking due to an earthquake. And we choose these points that in the narrowest point at the base. So therefore it's the backwards and forwards rocking direction that mean it will be most likely to fall over. And so the critical point for these rocks is where its center of mass has been pushed by the earthquake wave so that it's no longer being supported by its basal area. So as soon as the center of mass is outside of its base, that's when your rock is going to topple over. And so the amount of rotation of that center of mass that it needs to rotate through is captured by these alpha angles here, where the smaller an alpha angle, the smaller you need to move that center of mass before it topples over, so the more fragile the rock. And so for each of the rocks I study, I produce an accurate 3D model of their geometry so that I can then measure those parameters that I had in the previous slide. And so once I've measured them, I then use a suite of equations that have been previously derived by others, that essentially from putting blocks of rocks on earthquake shake table simulators, and these rocks have different heights and widths. And so they recorded when each one of those rock blocks toppled over. So basically I apply those same equations to my precariously balanced rocking rocks. And so what I then want to know is what is the probability of this rock toppling given a certain strength of earthquake shaking? And so I produce a plot like this, where the probability of the rock toppling increases as you go from the blue, where it's a probability of 0, where it's definitely not going to fall over, up through to a probability of 1. It's definitely going to fall over when you get into the yellow. And so I'm interested in calculating this over a couple of ground motion parameters. The first is our peak ground acceleration again. So this is just the size of the push that the earthquake wave gives to the rock. So you can see as the peak ground acceleration increases along this x-axis, the colors change so the rock is more likely to fall over with a bigger earthquake push. Kind of makes sense. And so our other parameter that we're interested in is this ratio of the peak ground velocity to peak ground acceleration. And all this is essentially capturing is the duration that the earthquake wave is pushing the rock in one direction before it pushes it to rock back in the opposite direction. So as we increase up this y-axis, we can see that as the rock is pushed in one direction for longer, it's more likely to topple over. So that's the first step in our fragility analysis. As this is a really important modification to the methods that really improves our study over what's been done before, that we can see from our blue to yellow probability of toppling plot, that if you had a peak ground acceleration way off this x-axis, so 1 or 2g, so it'd be something like your 2016 New Zealand Kaikoura earthquake or 2011 Japan Tohoku earthquake, the ground shaking would be so intense your rock would fall over with near certainty, such a large ground shaking. However, if we go down to our hazard curves, we can see that ground shaking of 1 or 2G is very unlikely to happen. So although that's 1 or 2G is likely to cause the rock to topple over, it is unlikely to happen at our site. And so it's actually unlikely that that earthquake event would be responsible for our rock falling over. So what we do here is we combine these two inverse relationships, the probability of the rock toppling and the seismicity rate of earthquakes at the site. And so we combine these together to find the sweet spot for that rock at this site, what ground shaking is most likely to have caused it to potentially fall over. And so that's what we do to produce our fragility function here, which is basically a cumulative curve describing that, which has a median value, which is its most likely ground shaking for that rock to fall over. And so for this example here, it has a median ground shaking of 0.9 G, so just less than gravity. So this is a pretty stable rock. 0.9 G, you'd be having buildings falling down at that level of ground shaking as well. But we've answered our first question, how fragile is the rock, by producing this cumulative curve with a median ground shaking. So to answer our second question then, how old is the rock? And to do this, we use a technique called cosmogenic exposure dating, which is where we study cosmogenic nuclides, which are really rare isotopes that form at or near to the Earth's surface due to the interaction with high energy cosmic rays bombarding the Earth's surface. And so when these high energy cosmic rays hit certain elements that are in certain rock forming minerals, these high energy rays impact the nucleus and cause it to fragment to form new elements. Some of those being our cosmogenic nuclides that we're interested in. And so in our studies, we use the rare cosmogenic isotope of beryllium-10. And so that's formed when cosmic rays hit oxygen atoms in common rock-forming silicate minerals such as quartz. And so the important thing here is that beryllium-10 is only produced by this reaction. So when we see beryllium-10, we know that this is how it's formed. And so what we do is we collect some rock samples from our precariously balanced rock, and as Imperial in our cosmic lab, we then process these rock samples to first of all get rid of all the other elements in the rock that aren't our beryllium. And once we have just our beryllium, we then sort out those beryllium atoms to see which ones are our rare beryllium-10 atoms and which ones are just the more common beryllium-9 atoms. And we do that using accelerated mass spectrometry. And so once we know how many beryllium-10 atoms we have, we can then calculate how long that rock's been exposed to the Earth's surface. But before we start just collecting samples, we first want to develop a geomorphic model of how these rocks are forming, so we know how to collect these samples and then model the data. So this is an example from the rocks in Southern California now, these granite rocks. And so from our observations, we interpret that when these rocks that are now at the surface were deep in the subsurface, that they were preferentially weathering along these joints and fractures that exist within the rock mass. And so this weathering then leads to this material becoming softer. So when the erosion rate then increases, this softer material is preferentially eroded and stripped away, leaving just more competent, precariously balanced rocks behind. And so by developing this geomorphic model of how they're forming, we've then developed a sampling strategy where we collect a vertical profile down the rock surface to sort of be able to track this lowering of the removal of this weaker weathered material through time. So this is just a simple diagram showing the same idea, where this gray material is slowly being lowering through time. And so the critical panel for our precariously balanced rocks is this fourth one here. And so that's where this gray weathered material has been lowered so that it's now has exposed the lowest point of our precariously balanced rock. As that means that surface is now freed up for the rocks to be able to rock backwards and forwards on its base and so potentially topple over. And so it started recording earthquakes at this point. And so our methods of modeling the beryllium-10 data allows us to solve for the rock's history. So we've got our beryllium-10 concentrations here, and this is sort of as you go vertically down the rock surface that we were sampling. And so we can solve for which beryllium atoms were accumulated before the rock was exhumed, so when it was sitting in the subsurface, how many beryllium-10 atoms were accumulated during the rock gradually being exhumed through that softer material, and how many beryllium-10 atoms accumulated when the rock's just been sat at the surface as we see it today. And so we combine this before, during, and after accumulation of beryllium-10 to get a total. And then what we do is we see how well that total matches our measured data. So we've got our green circles here, which are our measured beryllium-10 data. And then our red open circles here are the predicted beryllium-10 concentrations based if we summed this before, during, and after combination. And so what we do is we run a Monte Carlo simulation to optimize for this before, during, and after accumulation and erosion rates. And so to do that, we then get hundreds of iterations, and from that we can then calculate this T-tip age, that time at which the very lowest point of our precariously balanced rock became exposed, allowing it to start rocking during any earthquake shaking. And so from that we get a median, our best fit age, and we also importantly get an uncertainty on that age, which is also importantly a very small uncertainty. So we can really well constrain the age of these rocks, which is not something that's commonly done in previous precariously balanced rock studies. And so this is a key piece of data that really informs our work and also gives us confidence in our analysis. And so I've been working out the data for lots of rocks around Southern California, and the age of these rocks, a huge variety in ages, and they're ranging from thousands to tens of thousands up to 50,000 years old. We've been seeing rocks that have been precariously perched in the landscape, recording the lack of these rare large earthquakes. So now to combine our two pieces of information that we wanted. So we're going to combine our fragility function, how fragile is the rock, which was that, again, that cumulative curve with the median ground shaking for that rock at that site toppling. And we combine that with our fragility age, how long the rock has been there in the landscape. And so then we use those two pieces of information to individually test each and every one of these alternative branches through the hazard logic tree to see which one of these branches produce estimates of ground shaking that are too high to be consistent with our rock. So these are the branches that are producing the worst case scenario ground shaking, large earthquake estimates. And so when they're not consistent with our rock still standing, we identify them as incorrect and so remove them from our model. And the branches through our hazard logic tree that produce smaller ground shaking estimates and so are totally consistent with our precariously balanced rock still standing, we identify them as being consistent with our rock, so we keep these ones in the model. So basically we then rerun our model, getting rid of these inconsistent branches to then have a new improved hazard model. So this is our improved hazard model now. We've got our hazard curves again. This is the same axes, our peak ground acceleration and the annual rate at which that ground acceleration is expected to occur. So our black curves here are our original curves before our precariously balanced rock data. So they're the ones we saw at the beginning. And our blue ones are our new improved ones using our precariously balanced rock data. And so the first thing to say is that we've shown that the ground that the nuclear power plant site is on is not as hazardous as previously feared. So looking at this 1 in 10,000 year earthquake again, that our mean estimate, we've reduced from being over a G, so exceeding gravity, down to something like 0.7 G. So we've reduced the mean estimate by 27%, which in terms of the design criteria is potentially huge savings in terms of how robust you need to build this structure to be. The second thing our results show is that we've greatly reduced the uncertainty in estimates. So before I showed the range of the 5th, this dark blue, up to the 95th estimate. That was the original range in our estimates. Whereas now with our improved hazard curves, the estimates only range from this turquoise circle up to this turquoise circle. So our range has been reduced by 49%. So we can now make these hazard estimates with much more certainty than we could previously. So just a few summarizing societal impacts of what the application of our results can do as we look out over an auxiliary dam and reservoir in California that it was later discovered has an active fault running beneath it. So these are sort of projects where we really want to introduce our precariously balanced rock work. So the first thing to say is that the estimates of rare large earthquakes are highly uncertain. Our seismometers have only been recording for hundreds of years, whereas our precariously balanced rock, what's really exciting about them is that they've been there recording the lack of large earthquakes for tens of thousands of years, as this data just isn't otherwise available to us to inform our earthquake hazard models. The second thing to say is that by reducing the uncertainties in the future earthquake shaking estimates, it means that the design and maintenance and security of critical infrastructure projects can be made much more certain. So like, for example, our reservoir with people living downstream, that we can now be much more certain about the design criteria that we need to build those to withstand. And so final thing is that what's really exciting is that we're only just opening up the utility of using precariously balanced rocks and studying them in this way. That by advancing our fragility methods and the fragility age dating methods, that we're really only just beginning to understand what a fragile geologic feature is and what's the range of fragility and range of ages that is useful to us in being able to validate earthquake hazard assessments for the first time. And so I'm not sure if a take-home message is a thing anymore, since we're all at home, but if there's one sort of super simple, super concise take-home message, it's said by the title of our recent paper that earthquake hazard uncertainties are improved using precariously balanced rocks. Ooh, okay, I think back to you, Hilary, then. Thank you everyone for watching.
Anna, thank you so much. That was absolutely fascinating. I can see that the questions have been coming thick and fast while you've been talking. So I'm trying to put some of the questions together, particularly the more popular ones. And definitely an area that people are interested in is how common it is to find these precariously balanced rocks, in the sense that the sheer number of them gives you an accumulation of data that is of very high value to test earthquake hazard. So that's an area and an issue that quite a few people have asked about.
Yeah, so I think what's really interesting that even in my talk, just looking at the two studies, the one for the nuclear power plant site and then the one for in Southern California, those rocks are completely different. They're made from completely different rock types. So they're an amorphous silica chert at the nuclear power plant site, whereas they're a nice granite in California. That they've both been produced by completely different erosional processes. That I talked through the Southern California ones with the gradual lowering of that more weathered material, whereas the ones at the nuclear power plant site, they were formed by meter scale, big block removals, removing all the other cliff face apart from our precariously balanced rock. And the rocks are also in completely different geomorphic locations. The one in California, they're in like arid desert mountainous landscapes, whereas the ones at our nuclear power plant site are in a coastal uplifted marine terrace setting. So I think the point being that our methods are really versatile and adaptable to any rocks that we may find, and that actually the main criteria of these sort of like fractures existing in the rock that are nicely going to form tall, narrow blocks are actually very common in a whole wide range of rock types. And so essentially what it comes down to is just going out into the area surrounding your site of critical infrastructure or wherever else you're interested in with just the mind's eye to look for these features. And so I think as we've been doing more and more studies, we've been opening up our eyes just by looking at these features as to that there's a whole range of things that are fragile features that can be incredibly useful to us.
Okay, thank you. I can see that another question that's getting a lot of likes, Anna, is that, and this is another anonymous question, so I'm not reading out a name, is asking, how do you know that the rocks themselves have not changed shape over time, which would mean that obviously their fragility might have changed through time?
Yeah, so that's a really important assumption that we make, that the rock in its geometry as we see it today has been that way right back until the point at which it got its fragility at its fragility age. And so I guess the answer to this is that, so when we're going out and surveying a site to look for fragile features, we then only select the best ones from that population in our analysis, meaning that we're only going to use the ones where it's really clear that their sides have been nicely formed by joints within the rock mass. And so because we can see their sides still line up with these joint fabrics that then continue in the rock outcrop surrounding upper Carrossie bounce rocks, we can see that the distance between those joints on the rest of the outcrop matches the width of our rock. So we know that their shape hasn't changed through time. And so when you see the pictures of these really precarious looking, like really necked, narrow bases that looks like you might be able to push them over, that although they look impressive, they're not the rocks we're going to be using for our analysis, because it's obvious that their shape has changed through time. That's something we can't constrain very well. And so not only do we look for the best rocks that look like they haven't changed shape since they formed, we then also, if we can, try and quantify any erosion that may have happened at that site to modify the shapes of the rocks. And so at our nuclear power plant sites, we actually did a cool analysis looking at the volume of wet materials that was collecting on the ground surface below these rocks. And so by looking at the volume of that material, we could then calculate what the modification erosion rates might be. And so we could actually prove there in that case that it wasn't a big deal and wasn't actually modifying our rocks in a meaningful way.
Thank you very much, Anna. I can see there's a question from Scott, slightly more technical question, asking, does the PGA differentiate between horizontal and vertical acceleration?
Yeah, so in our case, we're just looking at the horizontal components, that we're just looking for that, again, if it's a force pushing that center of mass, essentially. And so one part of our analysis is that I don't know if you remember, that we think about our rocks in a two-dimensional way. We're just thinking about them rocking backwards and forwards. And so in that case, we can only think about one component of that horizontal acceleration, that horizontal one component moving in one direction. And so what we're hoping to do in future analysis is to sort of go into a more three-dimensional way of modeling the responses of these rocks, doing something like a finite element, discrete element modeling in an earthquake simulator environment. So in that case, we would be able to model all three components, the two horizontal and the vertical components of that ground acceleration, to really understand how it affects the rocking response of these rocks. Hopefully that should answer your question.
Thank you. I'm not sure how many more we've got time for, but there's certainly more questions coming up. Another anonymous one that's been heavily liked, Anna, is people are asking, how do you know that the rocks themselves haven't changed their shape over time? Because this would mean that their fragility has changed as well.
Yeah, so that really goes back to looking at rocks that we can match up their shapes to shapes that we see in the landscape. And so, as I was saying earlier, that we can then quantify those rates of erosions that are happening in the landscape around them to sort of verify that there aren't high erosion rates, so aren't modifying the shapes of those rocks.
You're getting a couple of people asking whether the Fukushima event was a 1 in 10,000 year event. I don't know if you can answer that, Anna.
No, and so all these things are about probability, right? And so that's why you get your range of fractal hazard curves, because you're going to put an uncertainty on any of these events. And so actually the Fukushima event, although a tragic disaster, gives us a whole wealth of data that we can then input into these earthquake hazard models, that by having all the seismometers recording the ground shaking from that event means that they can be piped back into the future earthquake hazard models. So again, piping that data in the same way we're piping upper Carrossie bounce rock data in, then allows you to in the future improve those earthquake estimates by just having more understanding, reducing that epistemic uncertainty with more data.
Okay, we have a question from Alan Gilbertson asking, is there a maximum conceivable PGA? Because that would be important to check that safety factors on the design case it's adequate.
Yeah, exactly. And so one of the places kind of where this study stems from, you know, that there kind of must be a limit you can place on the amount of ground shaking and earth a site is experienced, is also due to the fact that if you think back to our hazard curves, as you get right down that bottom right, you're estimating ground shakings of, I don't know, 5, 6 G, which in other studies would question whether ground shaking of that intensity is even physically possible. So that kind of like folds into our analysis where we're thinking there actually must be an upper limit on ground shaking that could happen, that we're not doing it from a sort of physical rock mechanics point of view, but in terms of our observational, these rocks are still standing and it looks like they shouldn't still be standing.
Interesting question from Phil Molicone. I hope I've pronounced your name right. Very heavily liked as well. To ask you, do you think that your approach could be used around the Mediterranean area? For example, using archaeological ruins like Roman or Greek columns?
Yeah, exactly. There have been other studies using exactly that idea. They're using the columns. Tombstones have also been studied, the toppling of tombstones during earthquake events. So yeah, exactly the same idea where you've got a tall, slender object that, again, if you put a force through its center of mass, it's going to topple over during earthquake shaking events. So yeah, exactly right, exactly the same idea. And so in fact, what we're hoping to do in future studies is to sort of combine the idea that, so at the moment we go out and look at the rocks that are still standing, but we'd also then like to go out and find a site where we've also got rocks that have fallen over. And so if those rocks that have fallen over, we can then reconstruct where they fell from, and so work out how fragile they were before they toppled, and potentially even date when they toppled. When we then come to test our earthquake hazard estimates, we can then actually say not only that this level of ground shaking has not happened because these rocks are still standing, but this level of ground shaking has happened because these rocks have fallen over. And so that way we can sort of try to constrain from both sides. So I think by bringing in something, we've got our stable rocks, but by bringing in something less stable potentially, such as a tall, you know, Greek or Roman column, sort of really like opens up the opportunity to do that in the study.
Another very different question coming up from Ian Miller, who's asking, what influence, if any, do you think weather would have to impact on your calculations? For example, wet seasons or ice which might have lubricated the rocking surface or the interface?
Yeah, no, that's a really interesting one. That's kind of in part what, as I was actually saying earlier in my previous question, has actually hampered our studies of wanting to look at rocks that are toppled over. That if we see a rock lying on the ground, there's no way for us to, at the moment, pinpoint whether it was an earthquake that caused it to topple over. You know, was it a particularly cold freeze-thaw cycle winter, or some vegetation growing in that crack between that caused it to topple over? And so yeah, that's a really important question in why we haven't managed to look at the rocks that have toppled over yet. And so I think it's also then interesting that all those weathering processes are actually really important in how our rocks are forming. That when we find a new rock in a new site, new geomorphic location, we want to understand the climate and the weathering processes that are happening, the vegetation, the freeze-thaw, that are going to be influencing the formation of the rock. That not only is it weathering and climate that can be sort of removing the supporting materials to then form our rocks, but also interestingly that other earthquakes could be shaking away that material to form our rocks. So there's this combination and balance of factors that's both creating and destroying our rocks, which definitely is important to consider.
Thank you. Great. We've got another interesting question from Maurice asking, and this will be something I was also thinking about, what degree of variability do you get when you look at similar rocks in the same area, and what do you do about that variability?
Yeah, no, that's exactly right. And so what we want to do in our studies is when we go to a site, we want to understand the range of fragility at a site. So study the population of rocks that are there. And so due to the natural variation in the width of those joints and the rock fabric and texture, you are going to naturally have a range of fragilities and also potentially a range of fragility ages. And so that's really interesting to then combine, because if you then combine different rocks of different fragilities and different ages, you can then be testing different parts of those hazard curves. I'm not sure if you can picture it, but young rocks could be testing the sort of 1 in 1,000 year earthquakes, whereas very old rocks could be testing the 1 in 10,000 year earthquakes, for example. And so that's like really informative to actually have that range. And so we would argue to include all the rocks in that analysis, even down to that most fragile one. So that most fragile rock will be doing the biggest constraining on the hazard, because it'll only take a very small amount of ground shaking for it to topple over. But because we've understood the rocks and the way they form and sort of their variety across this site, we'll ensure that we're really as confident in that most fragile rock and the data it's providing right up to the most stable rock. So we'd want to include them all, but with that most fragile rock providing the biggest constraints on our hazard model.
It's worth saying that a lot of people, Anna, are beginning their comments and questions by saying how interesting this is.
Oh, that's lovely to hear.
But another anonymous one, but it's got quite a lot of likes, understandably, is asking, to what extent do you think you can extrapolate data gathered as you did in California to parts of the world such as Japan, which doesn't have the same geological formation? So would you be considering different approaches for different parts of the world, and what would you base that on?
Yeah, so the reason we're working in California at the moment is that the earthquake hazard model is one of the best in the world, that there's more known about faults there than most other places. And so there's lots of data for us to be testing. And so the beauty of our precariously balanced rocks is they do a really site-specific testing of the hazard models, that you're really understanding how the earthquakes are interacting and forming and the processes at that specific site, which is what you're interested in. And so the way we want this analysis to go is that, say, for your future nuclear power plant or your future hydroelectric dam, that you have a precariously balanced rock study as part of that. And so you go out around your site and look for precariously balanced rocks there to really test and really understand your hazard estimates there. That a lot of data from, because we haven't been recording earthquakes for that long, a lot of data that goes into earthquake hazard models, whether in California and Japan, comes from a global database, essentially. Because we don't have that many recordings in one location, we use all the recordings we have globally to kind of supplement and make up for that. And so by taking this global data set, it means you've got lots of uncertainties, but it means for your specific site that you're interested in, a precariously balanced rock could then test it.
Thank you. Asked by, so I'm just trying to work out where there have been so many different questions in so many different areas. An interesting one is, how would you know whether or not one of your precariously balanced rocks hasn't actually been toppled and relocated down a slope, for example?
Yeah, no, that's an important one, that not only can precariously balanced rocks toppled by earthquakes, but yeah, you could then have them kind of forming by earthquake events. And so I think in that case, it's that we'd be looking for ones that there are the signs that they're still in their original location, that their joints that are bounding their sides are still matching up with the rest of the outcrop around it, that we can see if there's any sort of fabrics or textures in the rock, that they're continuous across the rock and then across the rest of the landscape. And so we really want to be certain that our rock has been where it has for the amount of time that we are looking over before we'd want to actually incorporate it into our analysis. That is actually a very important step for when we're collecting our samples to date the rocks, that if we, say, sampled a rock that had tumbled over and then fallen in a different location, we kind of just get a garbage jumble of beryllium-10 dates, because it would be capturing lots of different exposure histories when it's had different places through time. So that's something we would potentially detect if something like that had happened.
Thank you so much, Anna. There is another technical question asked by Phil Morlicone, just how deep inside the rock can this cosmogenic B10 form? Is it restricted to the surface? How deep does it go?
Yeah, so basically these cosmic rays, basically the energy attenuates with depth. So basically it exponentially like decays with depth. And so over the first meter, couple of meters of the rock, basically the production rate of these cosmogenic nuclides will be highest at the Earth's surface and then tail downwards. And so that's a complicated part of our analysis for those precariously balanced rocks in California, where like the Earth, the surface is gradually changing and lowering through time, where that exponential curve is starting and ending through time is changing constantly. So that's a complicated addition we have in our fragility age modeling. And so, yeah, so the top meter or so is where these cosmogenic nuclides are primarily forming.
Anna, thank you so much. Apologies to those people whose questions did not get asked. I can see there are many and they're still coming, but that's a clear measure of the level of interest and the wide-ranging interest there is in this study and in your results. So thank you so much for that. It was truly fascinating. To wrap up, I would just like to also let people know that the next Science Breaks event will be taking place on Tuesday, the 9th of February, when Professor Gupta and Professor Sefton will be discussing the Perseverance rover mission and finding life on Mars. So that's really something to look forward to. Thank you very much, and thank you to all those who participated.